of preview chapter, section 6, we're looking at linear inequalities, less thans, greater thans, those kinds of things. And indeed, here's the first definition. An inequality is just a mathematical statement where instead of an equal sign, you have a less than, greater than, less than or equal to, or greater than or equal to sign. If an inequality contains only linear terms, essentially what you can do is solve it using the same steps that you would normally follow for an equation, with one important exception. If you multiply or divide both sides of an inequality by a negative number, you must reverse the inequality symbol. In other words, less than becomes greater than and vice versa. If you think about it, it makes sense if you think about just a simple example. Certainly we all know that 2 is less than 3. But look at what would happen if you multiplied both sides of that inequality by negative 1. Left-hand side becomes negative 2, and of course the right-hand side becomes negative 3. Which number is bigger? Well, negative 2 is bigger than negative 3. So what happened here is the inequality symbol reversed. That's just a simple little example to show you how it happens, but keep in mind anytime you're solving an inequality, if you multiply or divide by a negative number, you will have to reverse the inequality symbol. We'll take a look at a couple of examples. In addition to solving the inequalities, we're also going to practice something else. We're going to practice our interval notation, and then we'll also graph our solutions on a number line so we can visualize them. All right, in this first one, I want to get x by itself, so just like I would do in an equation, I'll start by adding 9. To get x by itself, I have to divide by 2. And this time I'm dividing by a positive number, so I don't have to reverse the inequality. I will simply get x is less than 7. This is what we would call our inequality notation, and it's one of several possible ways to write the solution to the inequality. Another possibility is to show the inequality that we end up with as a number line graph. If x is less than 7, I might say, all right, starting here at 7, I don't want to actually include the 7. X can't be equal to the 7. And we often show that using an open circle. It means get as close to 7 as you want, but don't actually touch it. I want all of the x values smaller than 7. And so I show my graph going that way. All the numbers less than or smaller than 7. Finally, the interval notation. Interval notation is always read from the left side to the right side of our graph. And we need to remember that all the way to the left, we have to sort of imagine a negative infinity. All the way to the right, we have to imagine a positive infinity. So reading this interval, the left end, if you will, is negative infinity, and the right end is 7. We can never actually reach negative infinity, and we show that with a parenthesis. Similarly, we never really reach 7. We can't equal 7, so we'll also show that with a parenthesis. This would be the way we show our solution as a graph, and this would be the way we show our solution using interval notation. All right, let's take a look at another example. We have 6 greater than negative 4x plus 14. And I'm going to start by subtracting the 14. So negative 8 is greater than negative 4x. Now this time when I divide, I do have to divide by a negative number, negative 4. And so when I write the next step, I'm going to be careful to reverse my inequality. The greater than becomes a less than. And so my final answer in inequality notation is simply 2 is less than x. We're going to go ahead and draw the graph and write the interval notation as well. But one thing I want to point out to you before you do, oftentimes people work better with graphs and interval notation if the x is on the left side of the inequality. If that's true for you, we can simply literally reverse the entire statement. 2 is less than x means the same thing as x is greater than 2. Notice x is still on the greater than side, 2 is still on the less than side. So those two statements mean exactly the same thing. Our number line graph, again, x can't equal 2, so I'll show that with an open circle. And then I want all the x's bigger than 2, so I'll show that as going off to the right, towards the positive infinity end of the graph. And again, I always read my intervals from left to right. So I'll start at the 2 and go out to infinity. I don't actually reach either of those values, and therefore I put parentheses on my interval. All right, in our third example, we finally see one where we have a less than or equal to, so we'll need to see how to handle that with our graph and notation, but let's go ahead and solve first. I definitely want to get rid of those parentheses, so I'm going to distribute. And I do tend to prefer to have my x on the left side, so as long as I got the choice, I'm going to subtract the 8x, bring everything over to the left. Negative 5x minus 12 is less than or equal to negative 2. So I have negative 5x less than or equal to 10. Once again, I find a situation where I'm going to have to divide by a negative number, specifically negative 5. So in my next step, I will reverse my inequality. And so the inequality form of my solution is just x is greater than or equal to negative 2. I'd like to graph that solution on a number line. You'll notice that I tend to just draw my number lines so that the number I need is in them. I don't worry about drawing the whole thing or equally on both sides of 0 or anything like that. And so let's see. Negative 2, because I can equal the negative 2, this time I'm going to show that as a solid dot instead of an open dot. That says, yes, you can actually touch it, can actually equal negative 2. And then I want x to be greater than or equal to, so I'll go this way. Again, towards the positive infinity side. And so my interval goes from negative 2 to infinity. The way we show that a number is included with interval notation is to use a bracket instead of a parenthesis. We never can reach infinity, though, so that's always a parenthesis. And there would be the interval notation form of the solution. Just like equations, inequalities can have applications, and so we're going to finish this section with an example of an application problem. A little while ago, we did an example where we were modeling sales for yogurt. And the equation that we got rounded off to 2 decimal places for yogurt sales in billions of dollars was n equals 0.19t plus 2.09, t being the number of years after the year 2000. We'd like to write and solve an inequality to find out what years does the model predict our yogurt sales to be over 5 billion. Not equal to 5 billion, but specifically over 5 billion. That's our signal that we're going to use an inequality in this case. So I really want the sales to be more than 5 billion. I'm going to take my sales equation, 0.19t plus 2.09, and again say that needs to be greater than, and because the sales were already in billions of dollars, I only really need to put in the 5 here. So we've got our inequality written. We just need to finish out by solving it. We're getting 0.19t is greater than 2.91. And then I'm going to divide both sides by a positive 0.19. And since I'm dividing by a positive this time, I don't need to reverse my inequality. And I'm getting about 15.3. So t is greater than 15.3. All right, when we're talking in an application like this where the t-values are years, we do tend to have to work with whole years because the sales are annualized. So I need to have t be the first whole numbered year, bigger than 15.3, meaning I'm going to start with t equals 16, or in other words, 2016. And then any year bigger than that. So for years 2016 and later. Our sales are predicted to be more than 5 billion. All right, that concludes not only this section, but our preview chapter on linear functions and their applications. And at this point, we'll begin to work on some videos for the main content of the Math 139 course.